Time to start. So hello, everybody. Welcome back to the online seminar on numerical in algebra. It's with great pleasure that I introduce today's speaker, David Keyes. Until 2009, David was at Columbia University, where he was intensively working at a scalable solvers infrastructure project. Then he left to help launch the university KAUST, Saudi Arabia, as founding dean. I'm pretty sure all of us have heard about KAUST. 11 years later, he has not made it back to the US, at least officially, but is back to developing scalable solvers infrastructure at KAUST, Extreme Computing Research Center. So it's very pleasing that today's talk will also focus on the key role of low-rank approximation in various high-performance computer applications. So it was very nice of him as a trade union with our last talk last July. So, but before we start, I would like to recall that the participants can ask questions during the seminar, either using the Zoom chat handled by Daniel Kresner, or using the YouTube chat handled by Bart van der Eycken. They would be answered either during the talk or at the end of the seminar. Dr. Waji Bukaram will assist David for technical questions. David, please go ahead.
I thank you, Valeria and NLA team. Hello, colleagues. This is an opportunity to present in a wonderful series. I've enjoyed most of them myself. Being adopted into numerical linear algebra is a happy part of my professional life. I was not born into it, academically speaking, but linear algebra is, as we know, an amazing attractor. It was my need for implicit methods in fluid dynamics and reacting flows that drew me into this universe of methods. And over time, they became more interesting even than the universe of applications that these methods enable. As Valeria said, I represent a team of researchers at KAUST called Hikma, Hierarchical Computations on Manycore Architectures. Hikma is the Arabic word for wisdom. I trust that you agree that hierarchical algorithms like the FFT, the FMM, multigrid, sparse grids, etc., encompass great wisdom. And my job in the next hour is to similarly elevate hierarchically low-rank methods of linear algebra. These methods don't need any human push. They are highly compelling and are bringing in a renaissance of numerical linear algebra. We will describe a software stack that extends them to GPUs and to large-scale distributed memory. Now, since the talk has a software focus, let me wish you all a happy Richie's birthday, the co-author of the C language with Brian Kernahan and the co-author of Unix with Ken Thompson, the first two things he did when he showed up at Bell Labs in the late 60s. So happy birthday, Dennis. This talk resonates with several ENLA themes to date. Low-rank approximation has been the subject of the last 4 talks, in fact, along with communication reduction in 2 talks, randomization in 2 talks, and architectural adaptation, which has been implicit in several talks and will be explicit here in terms of processor and memory heterogeneity, exploitation of low precision, going back to Nick Hyam's talk that started this series, and high-performance machine learning-oriented SIMT instructions, both commercial and proprietary, and how can we take advantage of them in numerical linear algebra. These working slides that I'm presenting from are in the doc directory at github.com ECRC H2 Opus. H2 Opus is the name of the hierarchically low-rank library that we'll be introducing today, which is part of the Hikma software suite. An improved set of slides will be posted to the NLA website after the Q&A. So my conclusions up front, and you can decide whether to stay for the full talk if these claims interest you, is that with controllable trade-offs, many numerical linear algebra operations do adapt well to high performance on emerging architectures. Through higher residency on the memory hierarchy, because the number of clock cycles to DRAM can be as large as 10,000 in these very high process count modern processors. They take advantage of greater SIMD style concurrency. and they can feature reduced synchronization and communication. Rank structured matrices based on either uniform tiles or hierarchical subdivision play a major role in this port. And rank structured matrix software is here for shared memory, distributed memory, and GPU environments. And many applications are benefiting, either in terms of accommodating the same size problem in much less memory and therefore running higher and faster, or in stretching the size of problems that can be fit on a given system. When we come to rank structured matrices, we will consider two types. A matrix can be considered rank structured, to paraphrase Wilkinson, if there are enough low rank blocks that it pays to take advantage of them. That was his characterization of sparsity. So we'll consider tile low rank, where all blocks are at a single level of subdivision. They could in principle vary in size, but they'll be uniform in our examples. And hierarchically low rank, where blocks are left at various levels upon recursive subdivision to get a desired distribution of ranks. And there are weak and strong admissibility variants of these, as is now well known. The weakly admissible blocks recursively subdivide touching the diagonal, and the strongly admissible subdivide based on a criteria similar to fast multipole, where the ratio of the max or average diameter of two clusters has to be small compared to the distance separating them. And so in this case, off-diagonal subdivisions can occur, especially in multi-dimensional problems. Hierarchically low rank linear algebra is actually more than 2 decades old, from the schools of Huckbush and Tertishnikov. But Fiedler actually defined rank structure back in a 9-page LAA paper in 1993. It's been a prevalent topic, as many of you realize, at the SIAM ALA conferences, including 4 mini symposia at the most recent meeting. A conceptualization of the way H matrices are constructed, this is not the good algorithm, but this is a good way to think about it, is you start with a generally dense matrix and you recursively subdivide until you find blocks that can be usefully represented to high accuracy with lower rank than full. Continue to divide the remaining blocks until you get close to the self-interacting or near neighbor blocks for which they're small enough that it doesn't make sense to pursue low rank versions. And then you take the union of these red and blue blocks, and that creates the hierarchical structure. Again, this is not the efficient way to do it. You'd be doing too many rank evaluations along the way. You'd prefer to start from a geometric basis, but this is a useful way to think about what you get in the end. Now, we could start with an example of Gilstrang's favorite matrix, the 1D Laplacian. It's trivially sparse and it's trivially low rank, tile low rank as a result. What is interesting is that its dense inverse shares the same rank structure. All these off-diagonal blocks are of rank 1, even though they appear dense. And if you think about why this is, if you know anything about the Green's function for the 1D Laplacian, it consists of a bunch of ramps. And that's a little bit of insight into why the inverse has this low rank structure. But this, of course, is constant coefficient, and you would prefer to handle it by fast multipole. The good news is that these methods of linear algebra generalize that intuition to variable coefficients and all kinds of other matrices. What kind of matrices? Covariances from statistics, integral equations, Schur complements of elliptic and parabolic PDEs, Hessians, fractional differential equations, radial basis functions, and kernel matrices are major examples. What are the complexities available from these rank structured factorizations compared to the straight dense LU or LDL transpose, whose operations are order n cubed, and whose storage is, of course, order n squared if fully dense? Tile low rank, as analyzed for the optimal rank, the optimal block size for the rank, rather, in an excellent paper by Amestoy et al. In 2016 in CISC, shows that the operation count can be reduced to n to the 2.5 and the storage to n to the 1.5. Of course, if k there, the operational rank is Of order n, this is no gain, but typically k can be of fixed order compared to n. And the hierarchically low rank analysis, which is actually much earlier, shows an operation complexity of n log squared of n and a storage that's linear in n. And we focus really on the storage complexity, since that's what makes these algorithms especially interesting for the low storage per core environments of modern, of emerging architectures. Now, of course, these structured rank matrices are also relevant to sparse problems because they fill in upon elimination and the formation of Schur complements. So we know that for a 3D Poisson solver on a cube, classical nested dissection generally requires order n squared operations. Tile low rank, as shown by Amestoy et al., can reduce this to n to the 4/3. And Bebendorf and Huckbush showed way back in 2003 that this 3D, for example, Poisson solver can be solved linearly in the total number of degrees of freedom. What kind of applications are ripe for these methods? Anything with a memory capacity constraint, such as geospatial statistics with millions of correlated measurements, or PDE constrained optimization, where a full PDE discretization appears inside of an optimization loop. Anything related to energy constraints, where GPUs are relevant, or the new ARM processors, such as remote telescopes. We have software running on the Subaru telescope in Hawaii and is being used for simulations for building the European extremely large telescope. These methods of adaptive optics correlate tens of thousands of deformable mirrors to perfect an image with respect to atmospheric turbulence. Real-time constraints, such as decoding multiplex wireless signals. Runtime constraints, such as in chemistry or materials, not highly scalable in terms of number of cores, but long running. And they can be, the eigensystems, for example, of Schrodinger's equation are amenable to these rank reduced treatments. And of course, genome-wide association studies, which are growing in size to populations of entire countries in some cases. We're going to motivate a lot of what we do from geospatial statistics. It's an important application in Saudi Arabia for the siting of renewable energy, such as wind and solar farms, infrastructure in the billions of dollars. It's also relevant for smart agriculture, for weather-related tourism opportunities, for actuarial calculations, for property as the climate changes. And one of the authorities in this business, Dorrit Hammerling, last summer at a major geospatial statistics conference, said, she bemoaned the fact that we now have lots of data sets with millions of observations, but they don't really fit on people's computers. Indeed, a million by million dense symmetric double precision matrix is 4 terabytes taken at face value, and would take an exaflops to factor by conventional means. So statisticians take a lot of shortcuts, which are accuracy endangering, including hypothesizing global low rank, which is really not a useful assumption in most cases, or to zero out the outer diagonals. Better approaches would be to go to hierarchical low rank structure, or to reduce the precision of some of the weak correlations in the outer diagonals. And we're working on both, but we'll concentrate only on the former in this talk. I would submit there are many motivations for rank structured matrix software. There's the mathematical aesthetic. These methods are beautiful. They are the generalizations of fast multipole. They exploit the underlying structure. There's the engineering aesthetic, that they're efficient. They allow tuning to the storage and tuning of storage and work to the accuracy requirements. They don't oversolve or over-represent. There's the software engineering aesthetic, that we get to reuse lots of cool stuff that this community has invented. Direct and randomized floating point kernels, tree traversal algorithms, task-based programming models, much of which has already been ported and is available on new systems in the form of BLAS and so forth. There's the architecture requirement that we have to meet these architectures with limited fast memory per core on their own terms and take advantage of the new instructions they supply, like the 64 operations in one instruction of a 4x4 matrix multiply and add, which is a fundamental part of TPUs and other machine learning oriented hardware. And finally, there's the applications opportunities as cited. Now, let me give a couple of slides just to dwell on the architectural motivations. Some of the universals that we all face in porting to exascale. We need to reside high in the memory hierarchy to avoid the latencies or to cover the latencies to DRAM. We need to rely, or we should rely, on these new instructions that are useful for batches of similar tasks at fine scale. We need to reduce the synchrony of a billion core algorithm in magnitude or in span. We can have lots of locally synchronized operations. And we need to reduce the communication in number and or volume of messages, as so eloquently described in the recent talk in this series by Jim Demmel. There are many strategies already in practice to address these imperatives: exploiting extra memory to reduce communication volume, as in Demmel's talk; performing extra flops to require fewer global operations, like batching together many inner products in a Krylov method into one vector global reduction, and then doing the patch-up orthogonalization; use higher order discretizations to manipulate fewer degrees of freedom. That gives more cache reuse. The discontinuous Galerkin methods are a great example of that. Adapt floating point precision to output accuracy requirements, growing theory there, thanks to HiCMA et al. In this series. And take more resilience into algorithm space out of the demands on the hardware or systems space, where it is expensive in time, space, and energy, as pioneered in linear algebra of all computational domains by, for example, the group of Jack Mangera. Some additional strategies that are in progress with us are to use dynamic scheduling capabilities as much as possible, dynamic runtime systems based on DAGs to break global synchronizations, and the over-ordering that comes with triply nested loops and subroutine boundaries. Code to specialized backends while preserving high-level APIs for general users. Exploiting data sparsity to meet the curse of dimensionality with the blessing of low rank, primarily this talk. Process on the fly rather than storing all at once. You don't want to store that 4 terabyte matrix. You want to build it in pieces and compress it as you go along. And ultimately co-design with the hardware, including computing in the network or in memory. That's a new horizon made possible largely by FPGAs. I asked Karen Bergman of Columbia to update her famous slide by which she's been tracking 10 years of progress, or regress, we should say, in the ratio of bytes per flop available to algorithm designers. Both node power in flops per second and node bandwidth in gigabits per second have been improving over the last decade, but the latter much more slowly than the former, meaning that we can rarely use these processors at their peaks. And that is reflected in the degrading blue curve here, which is the ratio of bytes per flop. And you'll notice a very encouraging thing that occurred in June of 2020. The latest #1 machine, Fugaku, single-handedly raised that degradation of the ratio, got it a little bit back on the positive trend by having nearly 3 orders of magnitude improvement of on-node bytes per flop with the new ARM A64FX chip. So, but we still have to do, if you don't have $1 billion to build your own Fugaku, then the rest of us are still dealing with this degrading ratio and are highly motivated to have small working sets living high in cache and registers. So to achieve the potential for these key inner loops of computational science and engineering, we need to have tunable accuracy, space, time trade-offs, exploit a hierarchy of precisions. We may sometimes require more flops, but we complete earlier thanks to more concurrency. And an example of this, which I won't dwell on today, is the well-known eigendecomposition, or SVD, mediated by first a reduction to the polar decomposition, which is a highly concurrent algorithm as opposed to most of the diagonal chasing low concurrency methods that are out there. And this, of course, was started several years ago by Hyman Nukatsukasa, and is now one of our contributions to Cray's libsci. So there are these two universes of numerical linear algebra existing side by side. The one we think about, the one that's in textbooks, where we have nested loops over flat global memory, and the hierarchical one, which is in our software, where we have broken down those loops into small matrix blocks, which we can batch and execute concurrently. So this is the green field of which we wish to speak. Algorithms once were flat. They are conceived of that way. There's Cholesky's triangular recurrence. And architectures were once flat when all memory was equidistant and, for that matter, equally slow. So one hierarchy isn't so bad. As humans managing the complexity of these implementations, we would really like hierarchical algorithms on uniformly fast memory. We would tolerate, and we have, of course, done a lot of implementations. The early boots on the ground in GPUs were the flat algorithms. But now we face the meshing of these two hierarchies and the need to marshal irregular structures from the good algorithms into uniform batches and feed them to the architectures in dynamic runtime queues. Hierarchical algorithms on extreme scale must address the tension between the highly uniform instructions that prefer regularity and predictability and the efficient algorithms with tree-like structures and scale recurrence that possess irregularity and adaptability. So there's a large effort in H matrices, the undergirding theory, good new algorithms. There's a large effort in porting to GPUs and Manycore, and we're interested in that intersection in this talk. And no miracles will appear. It's a lot of hard work, but it's work in progress with interesting intermediate results in terms of high utilization of available bandwidth, which is usually the key to getting machine peak, and improved runtimes over conventional methods without contorting the application code. So here are some pieces of software you can find at the ECRC GitHub repository. Our spatial statistics package, which now has an R interface, our adaptive optics package, which similarly uses tile low rank linear algebra on the inside as well as mixed precision. The KBLAs, which complement what we discovered in KUBLAs several years ago, when we needed to have operations, especially that would achieve closer to the potential peak with symmetric factorizations. And these are now and have been for many years part of the KUBLAs. And in fact, NVIDIA has hired one of the two thesis students that designed these BLAs. And then the KSVB by Dalal Sukhari, which is now part of Cray's libsci, and some other packages which are still being implemented, not widely adopted yet, but a rank structured matrix library and classification suite, our API for runtime systems like Parsec, Quark, and StarPU, and the overarching HiCMA software stack. And today we're introducing the H2 entry into this, H2 Opus as it's called. And that's Waji's thesis project, and he will be online to describe its features as needed. So this is an H2 matrix computation library, hierarchical matrix multiplication with recompression because the blocks expand formally when you multiply them, generating approximate inverses by Newton-Schultz. Ordinarily, Newton-Schultz is not competitive for fully dense matrices, but once they are sparsified, it can be very useful, and therefore it can be used in the inner of the triple products that form Schur complements. Core utilities on which these high-level operations are built include the construction of the H matrix from matrix vector sampling, hierarchical sampling for the different levels that are pre-specified for the rank structures, low rank updates of an existing low rank matrix, sum plus xxt, for example, where x is low rank, matrix compression and recompression, orthogonalization of the bases that make up the SVD representations within each block, matrix vector multiplication, including blocks of vectors, and matrix construction from a specified kernel function as a convenience to users where those arise often, and the generation of the matrix structure from a geometric admissibility condition. It's built upon Magma, cuBLAS, and kBLAS for GPUs, and on OpenMP and Intel's MKL for CPUs. And there's Waji who'll join us. The zoology of H matrices, not comprehensive, but a good 2x2 classification scheme, is to look on one hand at the rank structure, weak or strong admissibility, and in the other dimension on the bases that are used to represent the low rank blocks, whether they are flat, constructed for each block by themselves, or whether they are nested. In the nested case, the bases for the larger blocks are assembled from the bases from their children, which results in a storage improvement and computation on the fly when the larger blocks need to be manipulated. So here is a picture of that schema. So you represent this hierarchically sparse matrix as a triplet of trees. That is to say, the off-diagonal blocks. The red blocks are represented densely. There should be a bounded number of them per row in a useful application of this technique. And then in each block, we store the SVD block, if you will, in blue, and the left and right column and row vectors, which are assembled from their children by means of these these E matrices, which also need to be stored. Now, we are, of course, hardly pioneers. This is a business that's 20 years old. Many people, perhaps listening, have contributed fundamentally to it, leading to the popularization of H matrices and their adoption. And you can see here some of the packages. I'm certain this is not comprehensive, but these are all publicly available packages on the left. Different techniques are described. In the second column, different formats, going back to that table of H matrices, or some of them are block low rank, and a paper in which an early appearance of the offering can be found. Now, of all these pieces of software, only HLive Pro is performance oriented for GPUs. So that's our niche, to extend a lot of this functionality to GPUs, backfilling where the cuBLAS didn't have needed things like QR or randomized SVD as part of their fundamental calls. Waji has built those along the way, and also extending to distributed memory, both clusters of GPUs, and even up to Summit, for example, where you have clusters within a node and MPI between the nodes, or NVLink. So the design strategies that we have over all of Hikma are to employ dynamic runtime based on distributed acyclic graphs where relevant, to break the tyranny of over-ordering in our conventional codes, or the unpredictability, really, of what operations will be available to go next, to co-design libraries to diverse architectures underneath while presenting a high-level API, and of course, in this talk, to exploit the data sparsity of TLR and HLR, meeting, as I like to say, the curse of dimensionality with the blessing that most physics that comes our way is amenable to low rank. So just these 3 points very briefly, and then we'll do sort of a pause, and then we'll talk a little bit more about the software and do a pause for questions, and then go into some examples. So taskification based on DAGs. Remove artifactual synchronizations in the form of subroutine boundaries, artifactual orderings, expose more concurrency. Of course, you pay some overhead for managing the task graph, typically 5% or so, and you potentially lose some memory locality if you move the blocks around. But within a NUMA system, you can move them around locally with good advantage. So a classical example, going back to 2012 out of the lab of Don Guerra, is this description of the generalized eigenproblem, where the first 3 steps are flop intensive, usually calling their own subroutine, shown in time from top to bottom and in concurrency from left to right in a very small instance. And one can, of course, use a DAG to increase the concurrency and shrink the sum of the heights, and so accomplish a good port this way. Co-designed to diverse architectures, this sort of follows the hourglass model of internet protocols, but here the advantages are coding to the details of the high performance architecture, getting into the ugliness of non-temporal stores, coalesced memory accesses, double buffering, etc. The code is more complex. It's architecture specific at the bottom, but you have ninjas doing their PhDs, and you can get this done so that many diverse applications are served by many diverse architectures through, hopefully, a fairly easy to use interface and an expandingly complex algorithmic infrastructure as you go down. Rank structured, we've already discussed their advantages at length. We want to shrink their memory footprints, reduce operation counts, and tune work to accuracy at the cost of compression or recompression. And not all operators compress well, random matrices not, but most matrices that arise in the applications that pay for the supercomputers tend to. So we want to replace dense blocks with reduced rank as they arise, high accuracy for exact solvers, low accuracy for preconditioners. Consider hardware parameters like cache sizes and warp sizes in addition to rank structure in tuning the block sizes. Use the randomized SVD, which is very gem intensive, blocks of vectors to form the low rank blocks. This is the Halko-Martenson-Trop algorithm from 2009, and implement for these SIMT style architectures in batches of leaf blocks where many blocks can follow the same set of operations at the same time, either natively in TLR or by flattening trees in HLR. So TLR is a nice compromise between optimality and complexity. You could say it became popular after HLR, not because it was better in complexity, but because it was so convenient to implement. And now, of course, it's useful to have both around, but with fixed rank, prescribed, you can get preconditioners. With variable rank, you can tune to the accuracy required, generally higher, nearer for blocks that are near each other, and sparser for blocks that are further away. H2 Opus is a performance-oriented library running on GPUs, with it, including all of the batch innards that needed to be brought into the Kublas. It can also run on CPU machines. It can present weak or strong admissibility. We prefer strong for the limited memory of GPUs. It bases that on KD tree partitioning. It can construct kernel matrices from a user-specified kernel function, and it's optimized for MATVEX, achieving up to 80% of peak bandwidth on GPUs. It can generate hierarchical orthogonal bases. It can compress. It can do low rank updates. It generates matrices from sampling, has a matrix-matrix operation, which can be useful in Newton-Schultz and Schur complements. So here I'm going to pause. I'm more than halfway through my talk, but this is the meat, and the rest will be examples that show hopefully some usefulness to all this philosophy.
Okay, David, can you hear me?
Yes, sir.
So there's indeed one question so far on Zoom. And the question comes from Fred Whoops, and he's asking whether the discretized incompressible Navier-Stokes equations have been addressed by a hierarchical matrix approach.
I don't know of an application paper that is high performance oriented that has done that. I'm sure in some of the existing packages that's been an example, but certainly the bottleneck for such solvers, namely the pressure solve, the implicit pressure solve, would be one that is readily amenable. Of course, there are many attacks on this problem in the Ellman, Wofford, Sylvester line of papers that show good ways of sure complementing that system. It's been very amenable, of course, to iterative methods after that, but some of the operations en route relating to the Laplacian are surely addressable in this context. We do have an LU version of these algorithms. It's not just for symmetric systems. I'll show one example of that. Of course, the symmetric systems are more common in covariance Hessians and so forth. But thanks for that good question. It's something I can look up and maybe add to the archival slides.
Okay, then there's another question by Piotr Luszczyk,
Yes.
and it's about the compression schemes typically used for approximating submatrices in hierarchical matrix format. So are the SVD and adaptive cross approximations the only compression schemes, or are there other compression schemes which play an important role?
Waji may want to compliment me, but I believe that our favorite method is always the randomized SVD. I think you have the ACA, or you've played with the ACA, right, Waji, as well as other more standard SVD methods.
Well, within H2 Opus, we're using rank revealing QR and the SVD, and we once had options for the randomized SVD, but with the randomized SVD, you end up with a lot of variance in the ranks depending on, because it's random, and because we take the maximum rank per level, that ends up inflating the rank a bit. So we ended up sticking only to either rank revealing QR or the actual full SVD. Okay, thank you.
Good. I'm glad. Yeah. So again, something I can look up. But the ACA is, of course, it looks very attractive. One has to develop one's own expertise on its accuracy tuning, like with all of these methods. In fact, if I resume now, the first slide I have is a caveat, which is basically an admission that we are applying these methods beyond the rigorous guidance that people expect of more traditional linear algebraic methods. We typically tune the accuracy of the rank-reduced matrix by block. In other words, each block satisfies a Frobenius or two-norm match to the block it replaces, but that doesn't necessarily address the kinds of errors that can accumulate when other operations like multiplication or factorization are subsequently performed. So there's a big need for theory to come alongside. What we do is we probably represent in terms of rank blocks in order to meet ultimate criteria, but a better connection of the compression to the ultimate accuracy requirements is a very ripe research field. But I will be careful to explain our accuracy limits in my examples. And I would say this is not a bad way to get started. It's similar to the compromises that people make in parallelizing traditional linear algebraic methods, where, for instance, the domain of pivoting is limited to something that's local, or the interchange local. So anyway, with that apology to the theorists in the audience, a class of problems that we find very convenient and often look at first are the geospatial statistics for non-uniform distributions, where a Matern matrix, either that's sort of an interpolation everywhere between linear exponential decay to Gaussian decay, is used to create a dense matrix. These applications come up in climate and weather, where the Matern is very popular. They always lead to evaluating the log likelihood function to optimize the parameters of that Matern fit. And you see here the sigma, which is the covariance matrix, whose inverse action and whose determinant is needed as the inner optimization loop, to evaluate the cost function. So these can both be obtained from Cholesky. So here's TLR versus Intel MKL on 3 generations of Intel hardware. The classical algorithm with its higher asymptote, and the low rank algorithm with star PU as the DAG based scheduler. And you can see in red the speedups that are available from successive generations of Intel hardware, from Sandy Bridge, Haswell to Skylake. You can see in green the speedups available on the same hardware for the improved algorithm exploiting tile low rankness. And of course, if you run the best algorithm on the newest hardware, you get to add those logarithmically or multiply them together. Here's an example on comparing to Scalapack on traditional distributed memory, where the Scalapack is run from 16 to 256 nodes, and the TLR Cholesky is run on just 16 nodes, and there's nearly 2 orders of magnitude for a 500,000 size matrix on 16 nodes. How does the memory footprint stack up for a double precision matrix of size 1 million? It's shown there at the top at 4 terabytes, and for a synthetic matrix or for a matrix from real statistics, you can see a couple orders of magnitude reduction in the memory footprint. A tour de force that was done by a combination of our team and Jack Dongarra's team on our Cray XC40 up to 4,096 nodes for a 42 million degree of freedom covariance matrix. It was accomplished in less than a day in either 2D or 3D as shown there. It would have required 77 days by the Scalapack algorithm at the memory enhanced TLR rate, and would have required 14 petabytes in dense DP, and most computers don't have that much DRAM, let alone that much disk storage. Here's the lone example of LU, and I'm very happy about this one since it was honored by the German Supercomputer Center with the Gauss Award in 2020 at the recent ISC meeting. This was for an exterior Helmholtz problem, boundary integral scattering equation, just the acoustic scalar case. And you can see here, if you look on, for example, the rightmost version, we compare the MKL Cascade Lake to the HiCMA on Cascade Lake for the generation in light blue and the generation and compression in the HiCMA version. So you can identify the compression overhead, and this here is a linear scale. And but you can see that after paying that overhead, the per right-hand side solve time is very much reduced. So typically in these scattering problems, you want to look at the same geometry from many angles. And this is a good reason to use a direct factorization as opposed to an iterative one, and good reason to go to compressed low rank. And this was a paper pioneered by 2 of our recent Saudi women graduates. And you know, again, this is an open access paper in the last ISC. So far, tile low rank, where we have n to the 1.5 storage versus the linear storage for an accuracy dependent K. So let's look quickly at one of the main targets that motivated us, which is PDE constrained optimization, in particular seismic inversion from the petroleum industry, where one has a data misfit from the model and the measurements, usually limited to surface, sometimes well boreholes, and a regularization term, and this is a cost function to be minimized. So the second variation of this gives the Hessian. The covariance matrix that arises also in Bayesian optimization is equally amenable to hierarchically low rank. The historic choices, and I look to Omar Gattas of Texas as one of the authorities in this business, a Bell Prize winning, geoscience inversions. You can either abandon prospects for dimension independent convergence rates by avoiding second order methods, or you can, as Omar does, use globally low ranked Hessians, which is valid for limited information. But that's often not where inverse problems want to be. You want inverse problems to use lots of information, which means high rank, which means hierarchically low rank is very useful. Now, I'm showing one slide here from a recent CISC paper from where this figure reappears, just to emphasize something that I'll waltz over in the talk, that when you do a MATVEC with these HLR matrices, you have the traditional dense part coming from the red blocks. And the other part is implemented like fast multipole, traversing a tree upsweep from find to course, applying the inner blocks along the way, and then downsweep to collect the results. This is magic as far as I'm concerned, as implemented and flattened by Waji, and then as put on distributed memory. He can talk about that later. But here are some results running on a P100 GPU for a 3D covariance matrix. This one from spatial statistics, showing the expected linear growth in time, contrasting the blue Kubla's oriented things to the red and black, which are two versions of the H2 Opus software. This is to a rather loose accuracy, relatively speaking, and a leaf size of 64, which is convenient for GPUs, and matrices running from 16K to 1 million in mathematical dimension, but never stored that way. What about the bandwidth for that performance? Here's the peak in green, and you can see that the HLR methods are a significant fraction of the peak, whereas the Kubla's based methods are just really wasting processor power by not feeding enough data quickly. And here is the multiple MatVec version showing the improvements that can be obtained by doing a block of right-hand side vectors. This is on GPUs and CPUs for a 500,000 size matrix. The GPU version obtains 90% of GEM at the high end. Here's H matrix multiplication, showing the expected linear rate, showing here two different tolerances for the blocks, 10 to the minus 2, 10 to the minus 4. Of course, time is a variable that you can tune the accuracy for. And here are the number of samples needed to get a good hierarchical result. These fast MatVecs can be used for fast inversions with Newton-Schultz. And here's the one example of distributed H2 Opus on 1024 GPUs from Summit. Recently, this was part of Waji's thesis. And here we see the batch size running from 1 to 64, the GPUs running from, I think, is it 1 to 1024, I guess, or 4 to 1024, and good linear behavior approaching the GEM peak, good flat scaling in the weak scaling sense. In the CISC paper, we have several small optimization examples just to demonstrate the principles of the compressibility of the Hessians in the optimization process. The one that I will focus on is a work of Stefano Zampini, our local PETSI and MFEM developer, who is now an H2 Opus wizard. And this is an example with water over sediments and a salt dome and a T-shaped anomaly, which is presumably petroleum. This is the target. And these are successive visualizations of this small 2D problem showing the progress of greater Newton steps, Newton iterations along the way. And this is an example showing the rank distribution of the Hessians at different levels. And this one is for a frequency oriented code. So as the frequencies rise, of course, the ranks go up, and there's a sort of a peak at intermediate levels. And this is in the new CISC paper about to appear. I don't think I have, in fact, I guess I've run out of time. So I will take comfort in pointing out that the last example is actually in the distribution at the H2 Opus repository. It is a fractional derivative application, both explicit and implicit. A fractional derivative is a Laplacian, for example, to a fractional power. The Laplacian is sparse, but any of its physically nearby discretizations are dense. And so you can see the contrast up to a few orders of magnitude in representing a 2 million by 2 million problem in 2D for fractional diffusion with rank distributions and so forth. Newton-Schultz can be used to build preconditioners for a PCG iteration. PCG does not converge on the native problem, but with relatively cheap H2 preconditioners, it's also a possibility. And this is in a recent CMAIM paper. So with apologies for exceeding my time, I'll just name some research directions. We need the heuristics or theory. We need, perhaps better orderings for the physical, problems that go into the matrix orderings, perhaps point block scalings for multi-component problems, and then some additional development to modularize, towards rank variability and to improve the parallelization beyond the sea level of these trees in the multigrid sense. I will skip my metaphor for flying to where the target is where it will be rather than where it is today in terms of computer architecture. I will credit my students in the top row for the results of this. Ahmed is with Jack's group. Rabab is still with us. Waji is going to Berkeley. Ali just went to NVIDIA from Jack's group, and the research scientists at the bottom who have masterminded this work. I especially need to thank Hatem Otayev and George Turkia for their vision and for their very effective coaching of the students. We have together had the opportunity to write a manifesto paper in a recent special issue of Phil-Trans. We thank our industrial sponsors. I won't recap the conclusions. I will restate them iconographically. We love TLR and HLR, and also we believe in these poetic descriptions of the beauty of low rank analysis of physical problems. Vast sea of numbers, can you be described by few as bones define flesh? So thank you for indulging me. And now, any further questions?
Thank you, David, for this fittingly high performance talk. Very enjoyable. And please, Daniel, are there questions?
So at the moment, there are no further questions on Zoom, but I think Bart has some questions on YouTube.
Yes, indeed. There's one question from Matt Knapley. So he's asking, is there any intuition when these hierarchical low-rank algorithms might beat more conventional algorithms like multigrid? And he's giving the example that probably for a simple enough Laplacian, a well-tuned multigrid will be better. So for what for types of problems are the hierarchical more suited?
Well, that's still something in the process of discovery. I think fast multipole and multigrid, they derive their intuition from the constant coefficient problems, from analysis of the Green's functions and the rates of decay of eigenfunctions and so forth. And whenever a problem has such ideal structure, it's probably overkill to go to these these algebraic generalizations. K has to be small compared to n, or the work of, that is to say that the maximum rank of the low rank blocks should not grow to be order n, or you're doing extra work to get the same quality of representation and extra work to apply it. One place where the low rank can win is in problems where you have many right-hand sides, like for instance scattering, where you have one matrix and many right-hand sides. Iterative methods don't typically take us full advantage of one right-hand side to the next as direct methods do. But I would say the reason that linear algebra is exciting is that there are so many methods, and one can pick and try on representative problems and tune for the best. So we're not saying that these are the best methods. We're saying that that software is increasingly available for large problems on large systems, and the more it gets used, the more questions like Matt's will be de facto answered. But thank you, Matt. Very good question. Of course, there's algebraic multigrid, as a generalization of that, which should never be used when you have the geometric available, but should always be used where you can't guarantee the contraction of the coarse space.
Okay, thanks. That's everything on YouTube.
Okay, Daniel, I think there's another.
Yeah, there's an additional question on Zoom by Alexander Litvinenko. It's actually two questions. So the first one touches open one of your last slides. I mean, just to clarify, did you actually try an H matrix approximation of the fractional Laplacian?
Of which Laplacian?
The fractional Laplace.
Oh, yes. Yes, absolutely. Yeah, in fact, that example is in the repo. It was actually done in 2 stages. This was done with a smooth particle representation. And the first stage is actually to do a interpolation. I think Chebyshev was used. And then to compress that result further using the hierarchically low rank. So this is here the relative times spent. This is the total time. This is the time spent on the interpolation and the time spent following that on the algebraic compression to ultimately end up with an HLR matrix, which was then used to compress the memory and to do either the explicit multiply U dot equals AU, where A is hierarchically low ranked, or to form a preconditioner for alpha I plus A, that diagonally augmented matrix inverse to use in an implicit version. So both are possible. I would editorialize that most fractional diffusion work to date has taken place in 1D. It's a hot area, but most people can't fit interesting problems that are both spatially resolved and dimensionally extended without going to these methods. They're very natural because if they work for the Laplacian, then they should work for a nearby Laplacian.
Okay, thank you. And the second question, he is asking about another type of matrices, but I have to admit I don't know these matrices, but maybe you know them. He's asking about inhomogeneous covariance matrices. And I think what he's meaning that if you have a kernel which does not depend on x minus y, but it depends separately on x and y.
Yeah. Okay. So yeah, this is a very good question. I'm learning more statistics, but not very fast. We have started with the very simplest case of a single field, not correlations between multiple fields in the same space, and of a single model that is stationary across the field. Now, non-stationary geospatial statistics, where the parameters of the optimization fit vary spatially, is interesting. So are they when they vary in time, as seems to be happening with climate change. And your question about inhomogeneous, where the actual kernel function changes from point to point, or where it doesn't depend on a simple displacement, that I have not heard of, but I certainly don't want to make any guarantees. But if there's still some kind of a physical dependence, where things that are near each other are more tightly correlated than things that are far away, no matter what the kernel looks like. If you have that fundamental, decay of influence, and if it's smooth, it's very likely that some blocking of an HLR matrix or TLR will win for you. But that sounds like an exciting frontier. So I'll look up inhomogeneous covariance.
I suggest that.
Okay, thanks. That was all.
I suggest that we wrap up and we give more information about the next talks. In particular, there are 2 new things that we'd like to share with you. So Elizabeth Ullman will give the next talk next Wednesday, and then we'll continue every other Wednesday. So September 30 will be the subsequent talk, so fortnightly schedule. And the other thing that we would like to mention is an advertisement about a young sister series of seminars on numerical algebra called the Communications NLA. And they already started last Monday, and it's on Monday at 3 p.m. Okay, with this, it's all. So we all thank you for the organizers for being with us today, and we look forward to Seeing you online next Wednesday. Bye-bye.